So this talk is not about Haskell. It's about something else. Should I go ahead or what? We'll just wait on. You can follow along if you download this thing, this little strip file. All right, go ahead. All right, so again, this talk is not about Haskell. It's about another programming language that is kind of like Haskell. It's about Coq, the Coq proof assistant. It's really about another language inside of Coq called Galena. Is much more like Haskell than Coq itself is. So I have some questions to start off, and then I will encourage you all to ask questions throughout. But who has used Coq, Agda, or some proof assistant like that? All right, a reasonable chunk. Who has not? All right. Who specifically has used Coq? And who would consider themselves a Coq expert? One kind of kept his hand. Okay. So feel free to ask questions about anything you see. You don't need to know Haskell. You don't need to know Haskell at all for this. You don't need to know Coq at all for what I'm going to show you. Some knowledge of functional programming and type theory would be useful. And if you have questions about that, I'm happy to stop at any point and explain anything that comes up on the slides. So that's the rule. You guys have to stop me if you ever don't understand something. All right. So this talk is about a technique called computational reflection. And computational reflection is something that we talk about in proof theory a lot, or sometimes, because proving things can be slower than programming things. And I'm going to give you an idea, a flavor of how this thing called, okay, so another question. The Curry-Howard isomorphism. Who has heard those three words put together? All right. So this is all what Coq is. So this is a definition. It's an inductive definition. If you're familiar with Haskell, this is like data, but it's a little bit different. Oh. Nah.
Move the window over.
Oh, that's the wrong window. All right, how about that? Good? Okay, so inductive definitions are kind of like data definitions in Haskell. There's a difference between them. They're actually inductive, whereas data definitions in Haskell are co-inductive. What this means is that, so this is a predicate. Even is a function from natural numbers to propositions. This P is the language of propositions. That's the language of proofs. This first constructor here, E0, says that 0 is an even number. The second constructor, ESS, says that if n is an even number, then the successor of n is also an even number. Okay? So you can encode this in Haskell with GVTs. There's nothing really particularly exciting about this, but this is the basics of what we'll be working with. So I like to do things on very simple examples because then you don't have to know anything more complicated. So in Coq, we like to prove things. And one thing we might try to prove is that 0 is even. We'll prove the predicate even 0. And in Coq, you can do this by using the tactic language, which is called LTAC. And there's a tactic called constructor, which basically will say, oh, I'll try E0 and I'll try ESS. And it turns out that E0 is sufficient for proving this. And you can actually look at what the proof is. You can say show proof. And it'll tell you, well, E0 is the program that you just wrote. And this is just like writing definition. Definition. 0 is even. Just type even 0. And it's just E0. So nothing exciting there. You can actually ask Coq, say these things equal each other, you can say goal 0 is even equals unnamed theorem.
It
Should let you name it. Unnamed if you spelled correctly. And you can actually ask Coq to simplify these things for you. Compute. E0 equals E0, well that's true. And there's a nice tactic called reflexivity that will actually prove things are true, or prove that A equals A for any A. So there I've shown you that my two programs are really the same. Oops. All right.
So, sorry. Looks like this would, this has a model where 1 is even, right?
No.
So there's nothing there that says that 1 is not even.
But there's nothing here that says 1 is even.
There's no way to prove
That's what I'm saying,
Yeah,
that you could have different models.
So
1 is even or not.
So what this says is it says there, so what we're interested
In other
in
words, is 1 being even, is that false or is it unprovable?
it's unprovable.
I think it's
Not
false.
false.
We
It should be
could
false.
prove that it is. We could prove it is false.
Yeah. Because the proofs are generated by it's the smallest.
I think we could prove it's not provable.
We cannot talk about not provability.
Within the system, you can.
We can prove that if you.
By demonstrating the contradiction part. So we can assume 1 is even and then prove also and then.
Yes.
And you can do that here?
Yeah.
Yes, you can do that here.
That's mysterious because I don't see anything about it.
So what's going on under the covers here is NAT is an inductive data type, also defined by an inductive predicate like this. You can print it. Print NAT. It says there's two ways to build natural numbers. 0 is a natural number, and the successor of a natural number is a natural number. So we're using Peano numbers, unary representations. And part of the notion of inductiveness here is a statement that says that this is the smallest set. This allows you to do pattern matching.
That's it. Thank you. We got to the end. So we can also prove that 4 is even by saying, well, constructor, constructor, constructor. Once we apply constructor once, that's going to apply ESS here. Now we're left to prove 2 is even. Constructor gets that. And then even, well, we know that. That's just constructor again. Coq thinks that typing things like that over and over again is boring, so we have a nice repeat function that'll just do it over and over again. And again, we can look at the proof here, show proof. And we get this nice ESS applied to ESS applied to 0. That's a term, and it's fully reduced. There's no, it's a value just like you would see in Haskell. Yeah? Could you actually prove that 1 is not even?
Yes.
What would that look like?
I'll work on it.
Let's see. All right, so you would write a theorem that says 1 is not even. And then it would say even 1 implies false. And if you can print false here, false is just like void in Haskell. It's an inductive definition, definition that has no constructors. How would you do this? Well, I think we could cheat and just get Coq to do it for us. Dependent destruction, probably. Don't acquire import program. This is not one of my fortes. I usually do it by hand. Show proof, if you're interested. That's what the proof looks like. Fun stuff.
The key is in the inner match.
Yeah.
Oh.
So we could write it by hand. If you're interested in writing it by hand,
I'm happy to do so. All right, so we will, well,
Actually, I was more interested in reading it.
I hate reading those things because they're usually terrible proofs. So H here will be a proof that one is even. We'll do it by refinement the way you would do like Haskell holes or something like that. So now we have H as a variable. What we're going to do is we're going to pattern match on that. And we're going to use something really fancy called dependent pattern matching, which is really very similar to GADT pattern matching in Haskell. So we will match on H. And there's two things about dependent pattern matching you get. You get to say what the type is going to be, even n. And that's all we're going to need here. So here, so that's just, oops, just argument. Oh, okay. So in this underscore hole, I get to describe the return type of my entire match as a function of n. Okay? On the outside, at the outside of this whole expression, I know that n is 1. Okay? But on the inside of my expression, I'm going to get to know that n is 0, or n is the successor of something. So I will pattern match on n here. So this is different than what you would see in something like Haskell, because here, this pattern match is at the type level. I'm writing a type right now. And what I'll do is I'll say, in the case n is 0, then I don't need to prove anything, because I'm not going to see this case. I can write true. And in the case that it's the successor, or sorry, if it's 1, then we'll write even
False.
I think.
You want false there.
I think I want that. And here I will write true as well. Now to read incorrect elimination of H, I have to say return prop. Even 1 is expected to have type false. Oh, false. All right. So, all right. Not sure why, but.
You're trying to prove false from H.
Oh, that's right. I'm sorry. You were right. I'm trying to prove false from H. So, what do I have to do? I get to pattern match on n. Okay, this is in the type level. So, the type I have depends on whether n is 0, 1, or not 0 or 1. In the case that it's 0, it doesn't matter what I put here. To prove it to you, I can write, let's see, something else, like 3 equals 11. Actually, I can't write that. 3 equals 3. It doesn't matter what I write here as long as it's provable. In this case, I'm going to have to prove 3 equals 3. That I can prove by REPL, which is just reflexivity. And here, I have to prove true. That we could also prove by I. So that's my proof. I can show it. And it's much simpler than what Coq generated for me. Does this make sense? A little bit? The trick, what we're doing here is we're using knowledge about, where's my cursor? Uh-oh. We're using knowledge about the type on the outside to inform what we produce on the inside. And we get to do pattern matching on this end in order to construct the return type of this. And this is a very crucial thing that we do in dependent type theory all the time. So this is your proof that says, if you have a proof that even is 1, then you can derive false.
Excuse me, just a question about the formal proof, since I haven't done it this way before. So what would happen if you wrote, 1 strong arrow 3 equals 3 in this proof? Like why does Coq refuse to accept a function here that returns something else in the case of 1?
Because you.
Right.
Right.
So what it's doing,
we return bottom proving false, but
Yeah.
We're just writing a function, it could have returned anything else. We chose that.
Yeah, so what it's doing is it says the type of this entire expression must be false. And on the outside, we know that the value, so the type of h is even 1. So this n gets unified with 1, and then we substitute n here. So this whole expression actually has type match 1 return prop with 0 implies 3 equals 3, and 1 implies true, false.
Right, but then, why does 1, what if we said 1 implies something else? Like, what if we said 1 implies true?
If we had 1 implies true, so
then we'd be, I guess then we'd be proving, trivial truth from our hypothesis.
So we're being obligated to construct a value of type false. So the type of this expression has to be a value of type false. Just like if we have a hole in Haskell that has type int, we have to put a number there.
Right, but
so the reason it works right here is because when you take this expression, match 1 with match 1 with this expression, this is actually equal to, we call it definitionally equal to false.
right, yeah. Of course, because you're selecting the one branch of pattern match.
Yep.
It's just that, and I think I'm getting at like the ex falso principle here. You could have written anything in place of that 1 and then just change what even 1 implies.
The inner match would be fine.
Oh,
Then it
sure.
would type check in that place.
Right,
Are you saying you could write this?
yeah, exactly.
Yeah, we could
Put
write
whatever
that.
you want there, and yeah, it'll eventually be true by ex falso. But that just sort of means that this proof seems.
Oh.
This just seems to be a form of proof where Coq will let
Your
us
type.
return whatever term we please, which
Your-
doesn't seem like a well-formed.
Your type at the
proof.
bottom.
Maybe could
Your
you
type
explain
signature.
What's
Oh,
going
yeah.
on
Sorry.
when Coq is checking type checking the inner match, or not the match n, but when it's checking that the body of your match h and even n actually does return.
Yeah, or maybe do the proof via a more elementary tactic or something.
So there's no more elementary tactic than refine.
How does Coq
Sorry.
check that the body of your match, which is E0 goes to E,
Okay.
but
So
ESSS goes
in
to
E0 goes to eCrefl, Coq takes this return clause and it looks at the type of the constructor E0. The thing on the farthest right-hand side is E0 or even 0. So it substitutes 0 for n here and then performs reduction. So that's why the type of this proof is 3 equals 3. Right? And that you could also write as match 0 return prop with
Right.
0 implies 3 equals 3.
Right, and so for the next one, it knows it's a form SSN,
Yep.
and that's going to match with the last branch.
Yep. So this is type match successor of successor of. Actually, I have to write this. So we get this n prime here. The successor of n prime. Return prop again with 0. It'd be nice if this type was shorter. Underscore error true. And this pattern matches out to the
So it just never has to check anything against it.
never has to check anything against false.
Could you use exact instead of refine?
Yeah.
It is more primitive. It's like,
So if you wanted to prove that even 501 proved false, you would only need to change the type check, but it would take longer for Coq to check.
If I wanted to prove,
You'd only need to change the theorem. The proof would work.
this proof would not work.
You'd have to go all through all the branches.
I'd have to
Okay,
go
one.
through a lot of branches here.
Yeah.
We won't be proving a lot of falses. We'll be proving a lot of other things. So I will table this discussion unless there are further questions about it. None of what we talked about here is necessary for understanding the rest of the talk. Wasn't expecting to prove that today. All right. I'm going to jump into the next bit, and you can pull me back if you want to talk more about it. So now we're going to prove that 1,000 is even. Thank God Coq has repeat, because it take a long time. So it took some time here. We can ask Coq how long it took. It took 7/10 of a second. It's
a lot better than 5 hours.
That's a lot better than 5 hours. Here's the proof. It's a super exciting proof. You can page down through it a little bit. Eventually, Coq gets bored of printing and puts ... there. It is a finite proof. It is 501 constructors long. But Coq is willing to build it for me. Thankfully, I didn't have to write it myself. And Coq is also willing to check that. So what's going on is, when you're running something inside of proof before defined, we're building a term. And we're type checking it kind of, but we're not like really type checking it. At the end here, we're saying, no funny business, really type check this thing. And that's what define does. So Coq takes about 7/10 of a second to build the proof. It's nicer because I didn't have to type it. It would have taken me probably a day to type that. And then it checks the proof in a half a second.
What if there are multiple proofs? I mean, if there's only one.
There are, so what if there are multiple proofs? Well, we're only checking one proof. This is like writing a function, and then, this is what, this show proof, which I guess we didn't show. This is the term we type check. Coq builds a model of that as an abstract syntax tree and then runs a type checker over it.
So it just sort of picks a model.
There is no denotational anything going on here. Everything is syntax.
Fine, but there could be multiple syntactic proofs of the same type.
Yeah, and we're only proving one of them. We're saying, is this E of SS, E of SS, E of SS?
Yeah. I'm just saying that in the case there are lots of them, then you would just pick them.
There's no picking.
Repeat constructor can only make one proof. Like, there are other kind of proofs we could make, but repeat constructor is just going to apply
So your
constructor.
tactics are deterministic.
They don't have to be, but these ones are.
So it is crucial
not important.
to separate one thing. Building this proof in LTAC is completely an untrusted thing. Only the type checking at the end is what we're going to trust. And that type checking is just like GHC type checking. It's completely syntax directed. There's no ambiguity going on. All right. So it's not a super fast system, but Haskell's not super fast either. So another thing that we could do is we could say, well, we know how we're going to build these proofs. So we could say, let's write a Galena function. You can think of it like a Haskell function that will build me a proof that, well, it might build me a proof. It's going to prove an option. This is like a maybe in Haskell. If it's given an n, it might produce a value of type even n, or it might say I couldn't produce one. And you can do this. It's a fun thing to do in Coq. We do dependent pattern matching here, and we produce some proofs. So now we can actually build the exact same proof, and I'll prove it to you. So prove even. This is just a little bit of LTAC. You can think of this morally like template Haskell. It says like, look at what I'm trying to prove and then run this thing on it. I can show you what it produces, as always. Show proof. There's our ESS, ESS, ESS proof over and over again. We built it a little bit faster, and that's because all these repeat constructors did a little bit of type checking, but kind of by writing it in Coq, we said you didn't really need to do that type checking because we knew what we were doing. So that was exciting, but it still takes basically the same amount of time to check it, and the reason it takes the same amount of time to check it is because it's exactly the same proof term.
Did you say that build even was using dependent pattern matching?
Yes.
In what sense is it dependent?
This is using something called the as clause. and it says option even n. And the as clause basically says the value of the, so we had in before, right, which allowed me to match the type of the discriminant. The as clause allows me to match on the value. It says the return type will depend on the actual value that I'm matching on. So in this case, it works the exact same way. In this case, I'm obligated to give a proof of type option even 0. In this case, I'm obligated to prove option even 1. And in this case, I'm obligated to prove option even s of n. Coq can infer simple pattern matches like this, which makes it deceptively simple. So there's our 2-second proof and our 6-second checking of that proof. And I said before that I believe these things are the same. Of course, Coq will tell us that, and it takes some time to do so, but for the most part, we're not going to be terribly interested in that. So there would be 2 ways to build this proof. One is using LTAC. That's what you would consider the standard way that Coq programmers would prove something like this. Another is using Galena, where we would build this proof in Galena, and then we'd be really happy because we can prove nice things like totality, even though our thing is not total. We can change this function to say, oh, you know, either n is even or n is even implies false, like what we did before. And we could change that function, and that would basically give us a totality thing that says any number is either even or not even. We can build that proof. All right. So you might ask, why is this checking this proof so big, or why is it taking so long? And I mean, it's a laptop, but it's not that bad. We can actually see what Coq is checking. Everyone loves this step. Show proof. So this is what Coq actually checks. It's the ESS constructor applied to this term is 998, and then the ESS constructor applied to this term, which is 996. And you can imagine that without the appropriate caching, which Coq does not do, type checking this might take a while.
So I can tell you that the time for define or QED is often dominated by the hash concert, which has nothing to do with type checking.
Aha. All right. Oh yes, you are Paul. What did I do?
I have a question.
Yep.
Is the complexity of the proof quadratic?
So the complexity of the proof is probably quadratic.
So like, can you double the 1000 here and we will see the time like 4?
Let's see. Building it doesn't take that long. Checking it doesn't take that long. Oh, sorry. I was in the next step. Building it takes some more time. No, 1.1 seconds. Checking it probably takes a little longer. 1.9 seconds. Yeah, sorry. So
That's the constructive. That's the quadratic.
that's the quadratic. All right. So I proved to you that we've built 2 different proofs or we built the same proof of this thing in 2 different ways, and I showed you that they're equal, which is great. We can take, so one thing is that the proof is really big. So one way we would opt to fix this is to say, well, what if we didn't have to build the proof? Then you might say, well, you know, you can't get away with that in something like GHC. If you don't have a program, then nothing to run. And yeah, you can't get away with it in Coq either. But what we can do is we can phase separate this. So what we're going to do is we're going to change this to, instead of returning an option of this proof, we're going to return instead true or false, bool. And when we return true or false, we're going to have to prove something after the fact that says, if we returned true, then there actually was a proof of even n. I just didn't build it. So what we're going to actually do is we're going to just separate this. So all of our trues are going to, or all of our sums are going to become true, all of our nuns are going to become false. And then later on, we're going to have to reconstruct that little bit at the top of it. So here is what you would write in something like Haskell. Check even, it's a little bit simpler. Tail recursive, even better. Because we don't have to produce anything at the end, except our bool. So this is super fast. the phase separation bit is the kind of annoying bit, so we have to prove that if check even returns true, it says for every possible natural number that you could possibly apply check even to, if check even returns true, then there must exist some proof of it. And this is just like a program in Haskell, so we actually have to show you this is the actual proof. We don't get to say like axiom of choice or anything crazy like that. We actually have to build it for you. And this is a little bit scary. It's because induction on natural numbers, like this isn't purely structurally inductive. You can see some fancy nonsense going on here. You can walk through it, but it's not really particularly exciting. So now we're going to prove, oh, sorry, I changed this from before. This is 1,000 again. So we can apply our similar tactic going on here. And now it completes very quickly. And we can show our proof. Show proof. And now our proof is really, really tiny. It says, well, the proof that 1,000 is even is the proof that check even is sound, and that that check even, let's see, that check even applied to 1,000 is equal to true. And Coq can simplify this by saying, oh, we'll just like kind of run it. And when we run it to a normal form, we get true, and then eq-refl will be a proof here that true equals true. And we can show you a little more detail here. Eq-refl is actually applied to true here. It says, well, it's applied to bool and true. And so this is saying eq-refl bool true is a proof that true equals true, and that is the same type, definitionally, as check even 1,000 equals true.
And so that the bulk of the work the type checker has to do is actually that type checker.
Actually in the reduction.
Right.
Yeah.
So the type checker runs your code.
The type checker runs the code, and that's safe because all Coq programs terminate. Not necessarily quickly, but they do. Will eventually terminate, and that's why it's safe to do
But
that.
it doesn't need to run check even sound, right?
Sorry?
It doesn't need to run check even
It doesn't
sound.
need to run check even sound. And so here we have this defined. It takes very little time, but we love proofs. And now we have to say, is that really small, simple proof that we wrote before, that really small but complicated proof with the check even sound actually the same as the ESS of ESS of ESS of ESS proof? And we can ask Coq, and of course it will tell us yes, because it is. So all it's doing here, you can ask Coq to do it for you. You can say compute, check even sound of, we'll say 500, and a proof of eq-refl. And that's what we get, this giant ESS of ESS of ESS of ESS. So everything I've showed you up to this point is the core idea of computational reflection. And computational reflection is about basically, I think about it as taking Coq's type checker, which is really cool, but really stupid, because all it knows about is the type checking rules for the lambda calculus. If we know something else about our domain, like the evens, which Coq, we would never expect to know anything about even numbers, because we expected it to know something about even numbers. We might also expect it to know something about odd numbers. We might also expect it to know something about C programs and all sorts of crazy things. It would never end. And the Coq developers don't care about even numbers as much as I care about even numbers for the purposes of this talk. We want to be able to extend the Coq checker so that it can be fast and it can check our proofs nicely. It's not as interesting to prove evenness, but when you get to large things like program verification, you could imagine something like evenness occurs quite frequently. With very large programs, evenness of very large numbers might occur frequently.
So,
Go ahead, Trey.
in practice, do you ever have to do the next step of actually evaluating the proof you generated? Like here, to compute reflexivity and to type check that, you needed to actually evaluate your check even sound. But in practice, with this kind of technique, do you?
No,
never-
you very rarely will reduce this proof. Most people would QED this proof.
Okay.
I'm currently on a crusade against QED, so
love to hear
I like
that.
to define everything. You have a question?
Does this expand the amount of the Cock implementation of trust?
No, not at all.
Why not?
Because reduction is already in Cox Trusted Computing Base. So the ability to, the same exact reduction that we did inside of this, I'm gonna caveat here, Paul can close his ears for a minute. The same exact reduction that occurred here is the same reduction that we're using to check that even of 1,000 equals true. Yeah?
So why did it not have to evaluate check even sound, but it did have to evaluate to a big term for your previous function? Was it because the option, like matching on the option to see if it gave you a proof,
Yeah.
to compute the entire term?
Exactly. So Coq is the reduction mechanism that we're doing here is actually strict computation. So EM compute is strict, and we're actually, so what's going on? This is like template Haskell. We're saying figure out what type I want, figure out the n, then compute this function, and the result is going to be some term. Template Haskell-y match on that term, find to see if there's a constructor of sum, like just. You get that proof and use that proof, whatever existed there, as the exact proof.
Okay.
So we're actually just doing some computation in template Haskell-y world, in LTAC world, but then we're just using that proof. So we actually do have to build it.
Okay.
Yeah. In the second version down here, we didn't have to build it until we did this bit.
Right, because you just check that the program you wrote type checks and has the right type.
Yeah. Yep. It's just like the idea that says, I don't need f of x, I don't need to evaluate f of x to know if f of x type checks, thankfully. Otherwise we'd all be in trouble. Any other questions? I appreciate all the questions, by the way, they're great.
What were you saying about define versus QED? Or if that's not relevant,
QED kind of makes something like an axiom that you've justified. So the proof is kind of hidden away. If I asked you, let's see.
You did another one of those proofs up above. You can see if they're equal.
Yeah. Are they equal? They should be equal. So even 1,000.
Yeah, they're both Ruffalo of the same term.
Of course, they're all named unnamed theorem something. So that's super useful to me. I guess I could say lemma foo and lemma bar. And this would be thank you. Oh, foo equals bar. I don't know if this will work actually. Yeah. Okay. So it can't reduce those things, and so it can reduce bar because bar is defined, but it can't reduce foo because foo is not defined. It's QED. And I think there might be some way that you can get the kernel to actually prove this, but maybe that doesn't exist anymore. Here is just me writing some things that we don't have to write this bit over and over again. So nothing exciting there.
So QED just kind of is an end scope for proofs?
Yeah, QED basically says like, I like to think of it like, it's like taking all of your other proofs and quantifying over a proof of whatever you QED. So no one else is able to inspect it because it's like it's universally quantified.
You could prove that previous proof directly with REFL, I think. Not as a tactic, but if you define it, right? Because the kernel has to be able to reduce.
We'll see. Oh, foo equals bar.
Maybe the elaborator gets mad for you.
Still doesn't like it. Ooh. Bar. Oh.
No.
There might be some way to trick it. I don't know. So, it turns out that, unsurprisingly, proving large constants even or odd is not the most interesting thing in the world. I know, gas. It's much more interesting and useful to prove like quantified properties, like for all n, if n is even, then the successor of the successor of n is even. We know that's true. In fact, we could have proved this by exact ESS, but I decided to get lazy. Let's see. Fine. All right, so we can also prove that large numbers are even if they don't look like large numbers. 200 times 200, that's a big number. We can prove it. Is even very quickly. But if you want to know what happened under the hood, what Coq did is it said 200 times 200 is some number that starts with a 4 and a bunch of zeros after it, 40,000 maybe, and then it ran check even on that, and then it showed that, and we can see if that's true. Show the proof. There's the check even sound proof. But when it's doing this reduction, check even, 200 times 200 must reduce to a number that we can match on. And so I guess I can't really show you how it's doing it, but it is actually reducing 200 times 200 to 40,000 and then checking that that is even. So, still quick, thankfully. If we had done that with the first or second group, we would have been here for a long time, which is why I don't do it. So the cool thing about natural numbers is we were able to match on them directly. Constants we can match on. If we can't match on, we weren't able to match on n here because n is universally quantified. If I had tried to apply my tactic here, my fingers in the right space, prove intros, prove even. Wow. Everybody knows how bad of a typer I am. It's not going to work because prove even r, it's going to match on this, and then it's going to match on this. And if we look down here, fingers crossed, we'll see that Coq was not able to unify true with this fixed point, which is matching on some number that we don't know about, n. And so it doesn't know which of these branches to take, and therefore it can't unify them. It's stuck. Yes. So that's cool. So when we want to prove universally quantified things, we have to do something a little bit more complicated, more sophisticated, and apparently we're not doing it here. But we can define a syntax for our terms. So this is basically a deep embedding of a programming language, and that programming language here is very boring because it's constants, it's plus, and it's multiplication. So this is just what you'd say. But then we can write a function that takes natsd, which is a programming language, and gives it a denotational semantics in terms of Coq's natural numbers. So this is a function that takes a nats and produces a nat. And it matches on the syntax s. It takes constants n to n itself. It takes plus ab to the denotation of a plus the denotation of b. And it takes mult ab to the denotation of a times the denotation of b. So standard denotational semantics, it's great because like no one thinks anything is going on here because it's just like plus equals plus. Yeah. Then we can write this little bit of template-y Haskell that basically says, if I give you an expression of natural numbers, then like 3 plus 5 plus 12 or something like that, or 3 plus 5 times 12, then I can build a piece of syntax from that. So this is morally a function that looks at a term like 1 plus 2 and converts it into one of these nat-s things. So again, kind of boring. But now we can write automation that pattern matches on that language instead of on fully reduced natural numbers. So now we can give a special rule that says, you can prove that a plus b is true without doing the addition, if you can prove that A is even and B is even, note this is incomplete because obviously it also holds true if they're both odd.
So in a real world thing for reify, would you like check for constants and all that and let those just reduce, or would you just, like if you actually had 1 plus 2, would you really want to make a plus 1 2, or would you want to just?
It depends. If it was like times 10,000 10,000, you would probably rather prove that 10,000 is even than 10,000 times 10,000 is even. But there is a kind of you have to pick one consistent way, otherwise you're going to be doing it yourself. Right. It's kind of boring. So multiplication is or. You can check if A times B is true, if you can prove that either A or B is true. I'll write some lemmas that are mostly boring. And then we can prove soundness again in the same way. Now we have, instead of a natural number, we have a piece of syntax that denotes the natural numbers. We have a new check even function on that syntax. Again, that's equal to true. And, sorry, we have a proof that that's equal to true. And even here is saying that the meaning, the denotation of n, is even. So it's actually pretty easy to prove this. This is just follows straightforward by structural recursion on the syntax of the natural number, this nat s. So when you do induction, it says you've got 3 cases to prove, and then you go through and you say, oh, well, let's simplify this, tell me what you need. Well, check even. We know that's true. We just proved it before. We got some rules about applying the lemmas we used above, but I didn't mean for anybody to actually follow that. There's a proof of this. We're going to define it again because we love defining things. This change goal tactics will change a goal that has even of something, like even of 200 and 200. I guess I can show you what it does. So before we ran change goal, we had even of 200 times 200. After we run change goal, we have even of the denotation of the piece of syntax that is multiplication of 2 constants together. And we can actually ask Coq to check this by applying our theorem, check even s, okay? That changes the goal to now, instead of proving an evenness fact, I have to prove an equality fact between 2 booleans. At the end, compute that, make true equals true, I prove it by reflexivity, and I prove it, and it's very quick. I think, if I recall, my tactic is called prove even r. So we can say, so that took 0.067 seconds, and I can do prove even r here. Prove even r. Oopsie. Find. Yeah. Maybe if we bump them up a little bit, we'll get more fun. At some point, Coq might just say, I give up, Stack Overflow.
It's a warning.
It may have just happened. Who knows? But maybe 20,000 is a little bit too much.
Or it'll eat your CPU, and you'll have to restart the computer.
Yeah. That should be quick. Checking 200 is took longer than I thought. This must be a unification thing. Okay, so we can do the same thing with fancy other things. Larger goals, quick theorems, lots and lots of fun. So now we've proven, we started with constants and we were able to prove them true. Then we said, okay, well, expressions are more interesting than constants, so we started being able to prove that they're even. That's cool. In my simple things are greater, we will now do tautologies. Again, something that we don't need. So we can define again a syntax of propositional formulas, true, false, and or, implication, and other. Here, this other means some uninterpreted symbol, so something that was probably introduced by universal quantifier. So that's something a little bit more interesting. We're not going to know anything about that other. It could be true, it could be false, it could be literally anything.
it's going to have a universal quantifier in a formula. So we're not going to know anything about it, but we will still be able to prove things like other implies other. If we had, you know.
What's the index type?
Index you can probably assume is something like an int. It's really positive, I believe. We're using this quote library, which does the reification step for us. And this is looking it up in that map. So what's the difference here is that now we're taking the denotation of a prop here, but we have a var map, that's a context that's going to map these indices into propositions. Here's our denotation function, and the quote library actually looks at this definition and tries to figure out how to reify it. So we don't have to make the reification magic here. We can write decidable equality. That's exciting. And a bunch of stuff about maintaining, oh, if I know all these facts, then I can prove things that are contained within those facts, and so on and so forth. So we can write this theorem, or sorry, this piece of automation. Given that you know all of these things in this known list, can you prove the goal? And this will be provably true. Again, it's returning a Boolean. And the proof of it is a little bit more complicated. It requires a few definitions. But there's the theorem. And if you squint, it looks very similar to what it said before. It says, for all goals, G, that's a prop, the syntactic version of prop, and hypotheses, that's our list of all the things we know, they're also pieces of syntax. Then if provably true of those hypotheses and that goal equals true, then for any instantiation of all the variables that occur in those terms, the denotation of all of the hypotheses conjoined together implies the goal. So it's a bit more complicated, but
more complicated, but the proof tactics are still pretty simple.
Yes, the proof tactics are still pretty simple.
The language is simple.
So there's our quote logic. Here's our goal. Lots of truths. Obviously, it should be provable. When we quote our logical formula, we get, so we've changed this to the denotation of something else. So it's an empty environment because there were no universally quantified variables. It's the implication of true and true and true implies true and true and true. Yay! We'll do it quickly by proving it, by appealing to our theorem, and then compute reflexivity. So it's the same exact story we've been, oh no. Same story we've been playing out all night. Compute reflexivity. So again, all the heavy lifting is done by this because we were able to teach Coq how to check these theorems for us. And we didn't have to rely on Coq to actually do the checking by building some large proof tree. So there's our find. So this is no longer called unnamed theorem 5, so I'm going to change this to 7. And now you might ask, well, the proof of that, let's see, oh no. Show proof of unnamed theorem 7. Oh no. Wow, I'm going to get this wrong a lot. I guess we'll just name it lemma L1. Now we can, oh, we can't say show proof. We say print. Print L1. So that was our proof. You might say, well, do we really care that we have this, like, is that really a proof? Do you have to know the automation? Because the automation that we use to build this proof is actually embedded inside of this. It's an expression inside of our proof. We can compute that automation away.
The name's wrong now.
Yeah, thank you. L1. And we'll actually get the pattern matched proof. This is what you would prove in Coq. It's not just an application of introduce something and then apply that. Because of the way the automation works, it actually says, oh, you introduced this thing and it's a bunch of ands, let's break it down so in case you need to use the individual pieces,
But that's what this is doing. It's breaking it down and then it's reassembling everything that it needs. So, how am I doing in time? So, everything we've shown so far. Oh, wait, so let's stop. Who's excited? Well, that's great. Are there any questions before we continue? No? I've amazed everyone.
Do you have examples with universal quantification? I mean, I assume it works because you have an index type and everything. But.
Yeah, so it turns out that the complexity of this is how complex can you make this term language?
Right.
All of our term languages up to this point have been relatively simple because they're all one type. So here, every expression in this term language is of type prop. In our old term language, every expression was of type nat. That's kind of simple. What if we had, nats and props? Things get a little more complicated. A lot of the complexity comes in defining this piece of syntax and then the denotation function. And then you obviously have to write the functions that actually reason about your syntax. But you could do something like you could reify, for example, GHC's kind of universe of type constraints. Then you could write something like a backtracking solver like GHC has. And you can solve GHC type constraints in a similar sort of way.
Question?
Oh yeah.
So, for in your previous example where you had like, you were trying to reason about like 40,000 times 40,000, and that was like incomputable, but you could do 4 200s in a row. Is there some way you could add logic or allow your program to reason about that and determine they could like show an equivalence there, or?
Well, you are limited a little bit by what you can do, right? Like, so the reason we moved from pattern matching on nats directly, S and 0, to pattern matching on pieces of syntax was we wanted to say, oh, here are the sorts of observations you can make about the expressions in your language. Okay, here's the way you build expressions, and now you can make observations about those expressions. To answer your question, like, once we have something, like, am I good at this tonight? When we have a p other, it's very possible that p other is used to represent something like true. But because we've reified it in terms of other, we can never understand that. Our automation is just fundamentally limited. And you can see that that's the case because if you look at the theorem that we're proving for any possible context that you could that you could use. So you might apply this to a particular place where you know that is true or you know it's false, but our proof is only working in a parametric way with respect to that context. So it's not allowed to inspect the context in any interesting way. Just knowing that it exists.
Could our nat syntax thing have like broken up, 4,000 into 4 times 10 times 10 times 10, and proven over that and made that trackable?
Yeah, we could have changed the automation inside of. So we could have changed two things. We could have changed the automation inside of check even s to do something fancy. Like, I don't know, suppose there was some very fast division function. We could have used that and said, if it's divisible by 2, then we're done. And if that was somehow faster than actually doing this, then that'd be great. And then we would actually have a choice inside of our soundness theorem. We could look at the soundness of that fast division algorithm and justify something using that, or we could attempt to reprove that. Because of the proof structure that we're working with, evens, you can prove that all proofs are equal. If I give you 2 proofs of even of the same number, they must be the same proof. But that's in general not true.
Well, that division statement is something that can potentially be derived from your original definition, right? Which is your successor function.
Yep.
So couldn't you, from there, like be able to reason about these more complex expressions and break them down? Or is
yeah.
that not within?
You can, so you can break down expressions, but I guess if you have a number that's like 10,000, right, and you want to figure out if it's 2 times 5,000, then you're going to have to look through the whole number 10,000 to figure out if it is 2 times 5,000. So you will be limited a little bit in that.
Seems like in the math syntax example, you gain a lot because your syntax is much more expressive than the actual constructors in terms of properties that are related to evenness, and it's also much more concise. But in the prop example, and maybe I just didn't look at it for long enough, it seems like the constructors you're creating are pretty similar to the constructors in the actual denoted language of Coq propositions. So what are you gaining here instead of writing like an LTAC tactic to do the sort of proof tech, like to just encode your knowledge in an LTAC? Because you can still destruct, or maybe I'm... Yeah,
so, and is an inductive type. We cannot pattern match on things of type prop.
Okay.
If I just know prop, I can't be like, is this an and or an or? Okay. I can do it in LTAC, but I can't do it in Galena. Okay. So yes, you could write this exact tactic, probably even much fancier than this, in LTAC. Sorry, not this tactic, this is the indentation function, but
the sound or the...
Yeah, you could write anything you can write in Galena, you can write in LTAC, pretty much. It'll be slower because you're going to build a big proof term and then check it, but you can do more because LTAC doesn't need to terminate and things like that.
And these proof terms are not, don't have the huge, they're bigger than they would be?
Yeah, these proof terms don't huge. These proof terms don't really simplify because like we're appealing to conj. Sorry, conj here is the constructor. It's like the pair constructor, and so we're just applying those sorts of constructors. The proof terms aren't really getting smaller once you reduce them, but you are like, if you had a big proof term and it was like, we do this all the time. I used to work in a logic called separation logic. We're basically reasoning about equivalence of monoids, and it's like permute this list, try to cancel things. Those proofs gets enormous, and computational reflection really is a win there. For the simple examples that we're doing here, to avoid having lots of complexity before we get to the interesting stuff, and to avoid places where it really shines. But there's work on like applying these techniques to like verifying C programs, for example. All right. So everything I've shown you right now is building a proof term that something is provable. You can also use this to do simplification. So rather than saying, oh, the proof is true, maybe you say, well, it's provable, but only if you prove this extra bit of stuff. And what's going on there is we write some functions. We're going to write a simplify function that now instead of returning a Boolean, it's going to return another proposition. So simplify takes what's known and a goal and returns another proposition. And the idea is the following. I could explain it to you, but it's easier just to read it. Simplify sound. It says, there's a bit of extra stuff. So it says, for all goals and hypotheses, the result of our simplification is going to be a result. And the way this works is the following. If you know all the hypotheses, and you know the result, then you can conclude the goal. So if we were to apply this, and I guess I can show it to you, it's usually a little bit easier. We're going to apply it using a lemma like this. We're going to have a goal that looks like prop D CTXG. We're going to apply this theorem. We're going to solve this bit via reflection, compute reflexivity. And then we're going to simplify this term. And we'll end up with something that is non-reflective, that doesn't look like syntax, but it will have this justified. So here's an example. We can prove for all propositions P implies P and true and true. I guess we should be able to get that. Let's see what happens. We quote our logic. Now we have this node VM. That's our context. That's our P proof. Simplify, apply. compute this first bit, well, that's just getting p other end ind g prime. So reflexivity solves that, unifying those two things. And now if we simplify just the denotation function, we're asked to prove p given p. And this is because my simplification doesn't actually use the context in the way you would expect it to. But we can prove it by assumption. So just to right, we applied our lemma that broke our one goal into two goals. One of them we proved by computation and unification, and the other we proved by, we reduced, and then we used Koch again, Galena, to prove the final what's left over. So this shows you that you could, if you had a really big proof that was composed of many boring parts and then a few small interesting parts, you could use something like reflection that would solve all the boring parts for you and then say, I couldn't figure this out, but if you can figure it out, the proof will be done. And that's what we're basically showing. Of course, it could have figured this out, but my automation was not good enough to figure it out. Oh, that's the end of the buffer. That means it's the end of the talk. Are there any more questions? Everybody's just eager to get out.
Are there like major open questions and computational reflection that are interesting?
There are some very interesting questions in it. A lot of work on open data types, things like you would have with the comp data package in Haskell, where you're saying like, oh, let me describe my language of natural numbers and my language of propositions, and try to glue these things together and glue the automation for them together is a very interesting open question. You get that for free in something like LTAC, because LTAC kind of just inherits Koch and is kind of untyped. But it turns out that like writing the denotation function for these sorts of things gets very complicated. I had some discussion about that on my website. That's what I wrote my dissertation on. And what other interesting things? There's obviously some very interesting performance questions about it. The reason this works so well in Koch is because Koch has this VM compute tactic, which basically compiles your code to a small virtual machine and then runs that virtual machine very quickly. If you were to do the same reflective automation but not use the virtual machine, it would be a lot slower.
If you use the kernel, you mean?
If you use just the regular kernel reduction mechanism. So there's some more work I know from France where they're compiling these things to native code. And it's interesting because while it's not explicit anywhere here, we know by virtue of the way we use this that when you simplify this thing, you will never have a stuck term. Koch's normal reduction mechanism works on open terms. If you have variables that are quantified, it's free to just reduce them, but those just get stuck. That actually makes reduction a lot harder, because you can't say like, oh, when I pattern match on something, I know it's a sequence of bits where the first thing is the tag and the second thing is not, because it could be an expression. So Koch's pattern matching, or Koch's reduction mechanism is not as fast as it could be if it knew things were just values. If you were able to do that, then you could actually compile this to be much faster. You don't have any uses for that right now, but there's some very interesting uses of this.
Is it always the tactic that's the slow part now? Like or is it the actual, like is the final actual proof? Like submitting the proof to the type checker, is that ever the bottleneck?
That is the bottleneck still. An interesting thing about computational reflection is when you do LTAC proofs, you can do a lot of search, and then you build a proof, and then you don't need to redo the search. But in the reflection world, you really do redo the search when you check the proof, because that computation is embedded inside the proof. So you get a smaller proof, but if you did a lot of searching, like you could imagine if check even was like triply exponential for some odd reason, then checking your proof would probably be a lot slower than Koch would, because building the proof tree is might be much smaller. You also don't get fancy things like parallelism, because there's no parallelism in Koch, things like that. There has been work actually that has shown that you can kind of use recorded traces of parallel executions as kind of like hints on how to guide your search, and that makes replaying the proof
much faster. But you have to represent all that information inside your proof. So it's a trade-off between time and space. Any other questions?
What's something interesting that you've proven using this technique?
Well, I went to Yale, and I talked to them, and they were like, that's super cool. And so they made some of their proofs about 100 times faster of their hypervisor. So Yale has built a verified hypervisor called Certicos, I believe. And you can download it, you can run it, it runs on x86, it can boot Linux, all sorts of things like that. It's like verified completely. They even have like crazy security proofs for it. Like we don't leak information between VMs and stuff like that. So super cool project. And while I won't say that my thing makes that possible, because that would be a way overstatement, I can say that my thing at least speeds up some of the proofs in that. The reflection work that we did with was big in some of Adam Srapala's work on Bedrock, which is a way to write verified assembly language programs. And on top of that, he's built many interesting things like a compiler called Ceto, and it was tangentially related to Fiat. I don't know the exact relationship between them, but that's about synthesis. So many things that you do in Coq are limited by the speed of automation, and you can use reflection in certain domains to vastly improve performance there. So, it is unfortunately, the downside is it's much faster to write a little pile of LTAC that solves most of these goals. It's only when you get to scale that you really see that it's more painful than you would like, it's slower than you'd like. You have a question, Mark?
Yeah. So you mentioned composition is an open challenge.
Yeah.
If one aspires to push out lattices of theories, of triples of types, operators, laws, and you want that lattice to compose nicely, are there any challenges other than composition? It's sort of like, I know this is the next project, I don't know the details on it, so.
Well, so I guess there's composition at two levels. One is the composition, like the normal programming language style composition. I wrote some language that has natural numbers and booleans and ifs, and you wrote some language that has like functions and some other stuff in it, and I want to glue my two languages together. That's like the open recursive data types with functors and stuff like that you could do. So that's solving, that problem applies only to the language, so like only like the prop language, gluing that together with NatS, and then composing the denotation functions. The other question, which is obviously very relevant to computational reflection, is how do you actually compose decision procedures? Which is a super interesting question. That's like something that people who do theorem proving, automated theorem provers are very interested in. And we have techniques like Nelson Opperman and DPLL and stuff like that. I have not implemented anything as sophisticated as that. There has been some work on an SMT solver, reflective SMT solver in Coq. Some cool work there. But composing that is difficult even before you do it foundationally. So I guess what I'm saying is that's a hard question, even if you don't say, and I'm going to prove it in Coq. So you can come up with two problems. One is, it's an easy problem, but then you decided to make it hard by saying, and I'm going to do it in Coq. Or you can say, it's a hard problem, and I'm going to do it in Coq. And the hope is that the latter one is actually easier than the former one, because Coq helps you quite a bit with that, paradoxically. Any other questions? No? Well, thank you so much. Oh.
Where do we get this quote library?
The quote library is part of the standard library.
Oh.
Yeah. So any installation of Coq will require import quote. I think it's red underlined, so there might be something wrong with it now. I don't know. It's been years since I've used it. Well, thank you so much. I appreciate the attention and all the questions.